with what we're doing now in 6.3, we need to, before we even begin talking about the fundamental theorem and anything, we need to really understand what an accumulation function is. And the question here is what is a function defined by an integral? So basically what we would have here is if we want a function defined by an integral, what that looks like is that you're going to have g of x equal to the integral from some a, and this a could literally be any a, to x of f of t dt. And there's some conditions we need where f is continuous on AB and x is in AB. So it has to be that, this x value is only from A to B, and it could be that f is continuous on R, in which case this will work. So now the key here is we sort of have some first geometric understanding, but also just know that it's really defined in terms of that limit x. So we're going to integrate from A to x, f. Right? That's the whole thing. Don't get confused by all these letters. But let's see what this means with a picture, right? So the general picture of this looks like this. So I'm going to draw the graph of f. This is going to be along t, right? And then this is going to be f of t, this value out. And then I'm going to have f, so let's draw f. Let's say f looks like this. I have no idea, whatever. And then let's say that this is a. And then this is some b, I don't know, way over here, let's say off of the chart. And what you're going to say is that what we need to see is that g of x represents the integral from a to x. So like here, if this is x, right, g is essentially the value of this integral from a to x, that area underneath the curve. And you could say, right, g of x is equal to that integral, exactly this value, whatever that might be. Okay, and that's the idea of an accumulation function. That's the general. Now the general might be a little bit more difficult to understand. Let's go through a particular case. So a good particular case would be if I said g of x is equal to the integral from, I don't know, 0 to x of, let's say, 3t dt. And in this particular case, it's sort of easy to make a nice little chart here and ask the following questions, right? So here's the chart, right? Here's my x values, and then here's g of x values. And let's say 0, 1, 2, 3, and I'll go up to 4, and that'll be fine. Okay, and we'll get an idea of what g of x is, especially after it is that I do a little sketch over here of what is happening. So let's do a little sketch as well. And let's see. Okay, so here's my sketch, and let's separate this. Okay. And what does 3t look like? 3t is just a straight line, right? So I'm graphing what this inner function is, what f of t is, right? So here's f of t, right? F of t, right? What's my f of t in this case? The 3t, right? That's a function of t. And what does that look like? 3t. 3t just looks like the straight line, like that. Okay, roughly, right? And I want to find out values for g of 0. Well, g of 0, what does that compute to? G of 0 goes from 0 to 0 of 3t. And we have a rule that says from a to a of any integral, doesn't matter, f of t dt, is 0. So this first value, g of 0, is 0. Now let's actually get to something that might be a little bit more illustrative. Let's say what g of 1 is. So g of 1 is the integral of 3t, right? This is 3t, from 0 to 1. So that's this area right here. And we should see that if t is 1, then this value out is 3, right? Because this is the function 3t. I'm trying to find out g of 1, which is, again, from 0 to 1 of 3t dt. And we should just see, what's the integral from 0 to 1? It's the area underneath this curve. It's the triangle. This is 3 times 1. And then divided by 2, you get 3 over 2. And I get that g of 1 is 3 over 2. And I could similarly do it for g of 2. So what's g of 2 mean? Well, g of 2 means if I go to 2, and then I draw this out, it's the integral from 0 to 2. It's this entire triangle here, where this height is now going to be 6. And it's going to be then this area, which is 2 times 6 divided by 2, which is 12 divided by 2, which is just 6. And then g of 2 is 6. And you could write that, I don't know, g of 2, right? Let's understand g of 2 is the integral from 0 to 2 of 3t dt. And then in that case, you find the area of this one. And you can keep going, right? 3. What would it be if it's at 3? Well, then we'd go up to here and we would find 3. This would be 9 up here, right? Because it's 3 times 3, which would be 9. And then 9 times 3 is 9, 18, 27. 27 by 2, whatever that is. 27 by 2. Okay, and then you could do it again for 4. So I guess I'll just do the math. 4 times 3 is going to be 12, somewhere way up here into space, and then I'm going to be looking at this triangle, right? 4 times 3 is 12. Don't forget this is 12 up here. This is a height of 12, and then this is 4. So 12 times 4 is or 12 times 2 is 24, and then your answer is 24, and then that would be that. Now, this is the general idea behind how we define a function by an integral, and that's an accumulation function. And with this in mind, we can talk about the fundamental theorem of calculus, the derivative part. So here's the statement of what the fundamental theorem is. The derivative part, if f is continuous on AB and g of x is defined as accumulation function on f, then the derivative of this g of x is just if I plugged in x into f. And this has, this has serious implications, and we can, understand what's being done here, because let's take our example that we had back here. Let's say g of x is defined as this function. What does this look like? If g of x is equal to 0 to x of 3t dt, right? Well, then what I have here is that if I want g prime of x, all I do is well, I plug in for x here, and I get that the derivative of g of x is just 3x. And this is nice, because now what we can do is we could answer a problem that involves an accumulation function like this. So here we have that the altitude of a drone is given by this accumulation function, h of t, and the variables can switch, right? So now the independent variable is t, right? So it's just like x, right? T, but I want to talk about how at any time t I could be given the altitude. So this h of t, if I plug in 1, that gives me the altitude of the drone at 1 second. So t is measured in seconds, and then the altitude is in meters. So at 1, I'd plug in 1 here, and I'd find out what this integral is, and then that would give me the altitude, the height of the drone. The altitude, the height, the altitude in meters, or the height in meters, whatever. Altitude, height, same thing. Okay? Now, if I want to, okay, what I can do here is I can, I have this, again, this is the height of the drone after t seconds. It's given by this, and u is just the sort of dummy variable, if you like, okay? It's given by this function. If I want the rate of change of the drone at t equals 3 seconds, right? This is the position, this is the height of the drone, right? And how do I go from position to velocity, or position to the rate of change of the height of the drone? Rate of change of the height, let's say height of the drone at t equals 3 seconds. Well, the rate of change of the height is going to be given by h prime of t. And by the fundamental theorem, this is going to be equal to this here with t plugged in, 32 minus 6t. And then if I want it at 3 seconds, I just plug in h prime of 3. And this will allow me to solve for the height. And then times 3. And then this is 32 minus 18, which is 10 to that, so then 14. Right? 14. 18, 32 minus 18 is 14. And that gives me that the rate of change of the height of the drone is 14 meters per second. And again, I just used the fundamental theorem to find the derivative of the position. This gives me the altitude, just the position along the y, right, or the height, the altitude in meters. What is the rate of change of the altitude, the height of the drone at t equals 3 seconds? Well, rate of change, derivative of position. The derivative of this by the fundamental theorem, since this is an accumulation function, is just if I plugged in t to this part here.